We are continuing with applications of the first derivative, and so we're going to extend. So in 5.1 we learned how to find the minimum and the maximum values on a closed interval, and today we're going to find the first step in finding the minimum and the maximum on the entire number line. Now we're going to not find that today, but we're going to work toward that. Okay, so first of all, let's just remember what it means to be increasing and decreasing. So a function is increasing on an interval if for x1 less than x2, then f of x1, the y-coordinate of x1 is smaller than the y-coordinate of x2. So it means I have x1 left of x2 on the number line, but yet f of x2 is larger. So this is my increasing, right? It looks like positive slope. And a function is decreasing in the opposite direction. So x1 and x2 still left to right, but this time my picture looks like this, where this is x1, this is x2, so my value of f of x1 is larger than my value of f of x2. Okay, so that's just a reminder of what it means to be increasing and decreasing. So we're going to use the first derivative to tell us where f, so we use the first derivative to tell us about where the function is increasing and decreasing. And so we say that if f prime of x is greater than 0 for all x in an interval from a to b, then f is increasing on ab. So if you think of it, right, f prime describes the slope at any given point of f. So if f prime is positive, then that means the slope is positive and it's increasing. So, and then by opposite, if f prime of x is less than 0 for all x in an interval, then f is decreasing in that interval. And then we just have one little vocabulary word here at the bottom. We say that a function is monotonic if the function is completely increasing or completely decreasing on an interval. Okay? All right, so we're going to use this idea to find the open intervals of increasing and decreasing on the entire number line. So I have some steps here that we want to use here. And the first one is to find, just like we did with when we were finding the min and max in a closed interval, the first thing is to find the critical numbers of f. So the critical numbers of f are either where f prime of x is equal to 0 or where f prime of x fails to exist. So let's find f prime first of all. F prime of x will be 3x squared, and then I'm going to have minus 3 halves times 2 is going to give me 3x. All right, so now I need to know where my function is 0. So my f prime can't change signs from positive to negative without passing through 0. So I need to find out, that's my next thing, is I need to find out, well, that's my critical numbers, right? So I set it equal to 0. So I'm going to factor out a 3x, and I get x minus 1. Don't forget the greatest common factors in there. This gives me x equals 0 and x equals 1. I'm setting this equal to 0 and this equal to 0. Don't forget about this one here. When it has an x in it, then I always have the x equals 0. All right, so this is like solving an inequality. So basically I have the 0 here and I have the 1 here. So what I'm going to do, I'm putting it on my number line, so that's the step 2. So we're going to put all the critical numbers on the number line and test a point in each interval using f prime of x. So we want to know the slope in each one of these intervals, and it can only change at 0, so these are the only places it can change. So I'm going to test, let's say I'm going to test x equals negative 1 in this interval. So this is just like a quadratic inequality. I'm going to test in the derivative though. It's going to tell me about the sign of the slope in f. So f prime of negative 1 is 3 times negative 1 squared will be positive 1 minus 3 times negative 1. So I end up with 3 plus 3. This is positive. That's all I care about. Okay. So when my f prime is positive, that means that I have a positive slope, which means that f prime is increasing, or f is actually increasing. F prime is positive. Right, so now I need to pick a value between 0 and 1. I guess the nicest fraction I can think of is a half. So f prime of a half, right, so I'm going to put it in to It doesn't matter which one I put it in, assuming I factored it correctly. So I have 3 times a half squared, which is a fourth, minus 3 times a half. So this is 3/4 minus 3 halves, and regardless of what my answer is, it's negative, because this one is larger than 1 and this one is smaller, right? The decimal approximation on this one is 0.75, and then this is minus 1.5, so it's definitely negative. All right, so let me choose a value for, oops, I need to use my prime symbol here, so then I'll choose x equals 3 here. So f prime of 3 will be 3 times 3 squared is 9, and then minus 3 times 3. So this is 27 minus 9, which is positive. That's all I really care about. So my intervals of increasing and decreasing using this, okay, so this is my next part. If f prime of x is less or greater than 0, then f is increasing, and if f prime of x is less than 0, it's decreasing. And so I'm pretty much there. I've got the signs here. And so I'm going to start using interval notation here. Now when we're using the increasing and decreasing, we never include the endpoints. We've kind of talked about that before, and this is not any different. So like this interval here, right, is from negative infinity up until 0, and we say it's increasing. And it's also increasing here, right? So from 1 to positive infinity. If you want to say x is less than 0 and x is greater than 1, that's okay too. And then it's decreasing in the center part where the f prime is negative, so between 0 and 1. We always use rounded parentheses here when we're doing increasing and decreasing because the square brackets mean that the point is included. Okay, so I'm increasing in these two intervals and I'm decreasing in this interval in the middle. All right, so again, right, we find the critical numbers of f, we put the critical numbers on the number line and test a point in each interval, we test in f prime, then we look at the sign in each interval. When f prime is positive, that means f is increasing, the graph is rising from left to right, and if f prime is less than 0, then we say that f of x is decreasing, meaning it's falling from left to right. Right, so let's do one that's a little bit more complicated. We're going to do the same thing, finding intervals of increasing and decreasing. So first we need to find the critical numbers of f prime. F prime of x, first of all. I've got a quotient this time, so I need the quotient rule. So that means I have the bottom times the derivative of the top, which is 2x, minus then the top times the derivative of the bottom, which is also 2x, over x squared minus 9 quantity squared. All right, so I never ever want to simplify the denominator, right? Because usually what we want to do is factor something, and this is already nice and factored. So I just want to open up my parentheses on top and see what happens. So f prime of x is, so I'm going to distribute this 2x through both. So I get 2x cubed minus 18x. And then on this side I get minus 2x cubed. Oh, how nice. So in the end I get minus 18x over x squared minus 9 quantity squared. This is my f prime of x, all nice and pretty. So now I want to find the critical numbers of f. So my critical numbers are either where my derivative is equal to 0, meaning where the numerator is equal to 0, so I get negative 18x equals 0, which gives me x equals 0. That's my first critical number. Or where f prime of x is undefined or does not exist. So that means I'm going to pluck out this denominator and set it also equal to 0. Again, I'm losing the exponent here because in my first step I'm going to take the square root and I get exactly this, okay, because the square root of 0, nothing changes when I'm using 0 on the right. So this is going to give me x squared equals 9, so I get plus and minus 3 as my critical numbers, okay. They are in fact all three of them critical numbers. Well, these actually will be vertical asymptotes, and hopefully you remember that as I approach a vertical asymptote, sometimes my graph can jump up or down. So my graph can definitely change from increasing and decreasing at places where my function is undefined. So I have some numbers on my number line. My next step, I've got 0 in the middle, I've got 3 over here, and negative 3 back here. So I want to test a point in each one. So I'm going to write, just at this point, I'm going to write each one of these intervals in interval notation. So this goes from negative infinity up until negative 3, this part right here, right? Because it goes out here forever up until negative 3. It's always smallest comma biggest in the interval. Then this new interval here goes from negative 3 to 0. Then this one goes from 0 to 3, right, from here to here. And then this one, last one, goes from 3 to positive infinity. So we're going to test a point in each one of these intervals. And we're going to use this nice, neat f prime to do it in. So I'll just try f prime of negative 5. So I'm going to kind of do just like I did before with inequalities. That's kind of what it's the same process. It's not really an inequality, but we just really care about whether it's positive or negative. So if I plug in negative 5, then my top will be positive because a negative times a negative is positive. I plug in negative 5 down here and I get 25 minus 9, and then I square it, so it'll definitely be positive. So this is positive in this interval. So I have found in between here, negative infinity and negative 3, I can see that my function f is increasing. Okay, so let's try f prime of, how about negative 1 this time? Right, I'm picking something in here. It doesn't matter what it is as long as it's not the actually endpoints, right? We don't want to use these because that's where my derivative is 0 or where it's undefined. So f prime of negative 1 is, okay, so I'm going to have negative 18 times negative 1, which is positive 1, or not positive 1, but positive overall, positive 18. F prime of negative 1, I plug it in down here, I'll get 1 minus 9, which is negative 8, but then I square it and it becomes positive. Right, so again, increasing in this interval as well. Now, negative 3 is a vertical asymptote, right, if we look at the original, because if I plug in negative 3, I'm going to get positive 9 over 0, which immediately tells me it's a vertical asymptote. Both 3 and negative 3 are going to be vertical asymptotes in this case. Okay, so that's kind of a good thing to know, so we'll put that there just for our future reference. All right, so now I need a value between 0 and 3. I'll just use 1 just to be symmetric. It could be 2. I guess I could choose 1.5 if I really want to, but I don't. So if I choose 1, I get negative 18 times 1, which is a negative on top. And then I'm going to get 1 minus 9, which is 8, but squaring it will make it positive. So it's negative in this piece. So now I found my first decreasing piece of my graph. And also this over here is a vertical asymptote. The reason I keep this in mind is because even though these side-by-side intervals are increasing, we need to write them separately because there's a spot here at 3 that's not increasing, right? It's actually a jump over a vertical asymptote. All right, and then I just pick a value in the last, let me choose f of 5, or f prime I should be writing, not f of. F prime of 5 is I plug in 5 and I'm going to get a negative value on top, and if you noticed, because of this final squaring, I'm always going to get a positive value on the bottom. So I'm decreasing down here. All right, so all I need to do now is write my intervals. So I'm increasing from negative infinity to negative 3, because this is the plus, and then from negative 3 to 0, I just use the u to attach them. And it's decreasing from, let's see, so I go from 0 to 3, and then I attach to it 3 to positive infinity. So these two, right, and I'm finished with my increasing and decreasing. So next time we will figure out how to find our local mins and maxes.